order is on page 57.
How narrated.
So on page 57,
tried to put all in the right direction.
you can see that length 3 is a freestanding color marker. The critical marker for us here is this one, which is 70 kilodalton. If you look at the marker page, the marker page is on 80. Yeah, freestanding color marker page is page 80, and you can see that the pink one is 72 kilodalton. Now, I'm going to give you more exact numbers here. I looked up the numbers. GAP-DH is 36 kilodalton, 36. And MVP is 32 kilodalton. So the fusion protein should be 68 kilodalton. Okay? Because GAP-DH 36, MVP 32, total is 68. Okay, the first lane here that's one of our sample lanes is the sample one before IPTG. So this is before induction. It's a little faint. It's probably been better to run more samples, but you can see that E. coli has proteins going from really big to really small. The lane next to it is after IPTG, and in the after IPTG lane, we have had a lot more growth, so we have more proteins, and you can see all these different bands. There is an extremely dark band here that's running suspiciously in the place where we expect to see our fusion protein. So that fusion protein has a promoter that I showed you before called PTAC. Remember that from the diagram? PTAC is not a natural promoter. It's an artificial promoter that's been constructed and designed to bind to RNA polymerase super efficiently. So that means you're going to get a lot of transcript of your fusion protein, and therefore, we suspect, make a lot of the fusion protein. And so I'm going to assert to you that I think this big giant blob here is our fusion protein. It's certainly much darker than anything else. And then all the other E. coli proteins would also be present because we didn't purify our fusion protein in the after IPTG sample. Now the next lane is the eluted GAP-DH sample. This was eluted from the column that's got the amylose. And so remember, this was our purification. We bound our fusion protein to the column because the MVP bound the amylose, and then we washed out all the other E. coli proteins, and then we used maltose to make the column let go of our fusion protein and eluted it out. So this is our flow-through that we recovered from that column. And again, you can see this really dark prominent band, and you can see that a lot of the low molecular weight stuff is gone, the high molecular weight stuff. We're seeing this band, and then a couple of other bands, and we'll talk about it. I'll come to that in a second. Then the next band is your concentrated product. And so this was after we took your protein that came off the column, and then we concentrated it using those Amicon rocket columns. We went from about a 1 or 2 ml sample down to about a 70 microliter sample. So this is much more concentrated, and now you can see that blob is huge. And you see a couple of other bands here. Now, remember, E. coli isn't necessarily fond of your foreign protein, and so you do get some degradation. This is a degradation product that we always see, and then we see a few other fainter bands. So that's due to a little bit of degradation of the fusion protein. But the intact fusion protein here certainly makes up, I don't know, 95% of the protein or 98% of the protein columns, did their job to give us our fusion protein. And so we know that you made a ton of this fusion protein. And so now the question is that fusion protein, does it have gap pH? And we're gonna answer that, on the western blot. Okay.
Just wondering, so when you say lactic repressor, is it kind of everything?
No, the lactic repressor is in front of
That's
only our fusion.
Why is it then producing all the others?
Because all the other proteins are not regulated by IgG,
yeah.
so any protein being made by E. coli will be present.
So that's why you meant the first one first and then the top.
Yeah, I mean, before IgG, we should have seen the same protein array that we see here, except that we wouldn't see this
Okay.
because we hadn't turned this gene on yet. I'm sorry.
Hypothetically, if we want to cleave the molecule from our gap pH, how would we actually purify something like that?
Yeah, so, let me see if there are any other questions about the gel, and then I'll go to the diagram and explain that. Any other questions about the protein gel? So this is an impressive amount of protein. If you look at this, if you look at this lane, after IgG, you can see that your protein is making up a substantial portion of the total protein that E. coli is making. So E. coli is investing a lot in making your protein, and that's because we gave it that really strong T-tag promoter. And so we're getting a ton of transcription and translation. The other thing we can tell from this is that your protein is successfully in solution. It didn't form one of those inclusion bodies where the proteins get congregated and they form this sort of insoluble mass. Because if we had inclusion bodies on protein, it'd be up here stuck in the well. So it's in solution, and that's good news also. So not only did you make the protein, the fusion protein, but it's the right, I mean, we got the right size, but also you can tell it's in solution because it's running according to its true molecular weight and not up here someplace. So that's good. So experiment one, our big giant experiment that we worked on throughout the whole course. We think we have success because we think we've made fusion protein, but before we declare 100% success, we'll wait to see the results of that. Another question? Very good.
No, it's
Okay, thanks, yeah. Anything else? Okay, so let me get to Sid's question. So, so the way you did the purification is we eluted with maltose and we got your target protein, which is gap pH, fused to MVP, or at least we're pretty sure that's what we have. If we had enough time, what we would do is cleave with that factor 10. That would release our target protein, which is gap pH. And then we could purify the target protein from the MVP by putting it back on another one of these columns. The MVP would bind, your target protein would flow through, and then you have your target protein. So it's really easy to do. We just don't have time to do it, but it's trivial. And if you get the tip from NEB, the instructions for doing that are quite clear. Okay? Any other questions? Okay. Oh, yes, Rob.
So, is there a way to predict beforehand whether you'll get a soluble protein or?
No, I wish. Maybe there are protein people smarter than me that might be able to guess, but I don't think there's any definitive way of knowing. We've been lucky. We've made a lot of different proteins that way, this way, and all of ours have been soluble. So I'm not an expert about how to deal with inclusion bodies or your protein not wanting to go in the solution or being misfolded or other problems with degradation, for example. We see a little degradation. You saw that, but not much. It's really good. That's about as good as you're ever going to get. Okay? So pretty successful. I'm really happy about that. Any other questions on experiment one? We'll come back to this when we do our get our Western results and we see if our monoclonal anti-gap antibody binds to that that fragment that we believe is the fusion protein.
So the target protein requires post-transcriptional modification.
Yeah, if your target protein requires post-transcriptional modification, that's not gonna happen in E. coli. There are, in vitro systems for making modifications. You can also, use, as a host, you could use yeast. Yeast will do some of your modifications. There are, vectors, expression vectors for, making your protein in insect cells, which will also do, some of the modifications, or most of the modifications. You can also use mammalian cells, it's just kind of harder to deal with, right? So, E. coli is the easiest, that's your first option. You need some modifications, try yeast, that's second easiest. Then baculovirus, which is the insect cell system, that's the third easiest, and then finally, doing it in mammalian cells if you have to.
When you're trying to detect whether you've made a protein or not, when do you use, Western versus doing like a protein ELISA from the supernation protein assay?
You could do either, we like to do the Western because you get a nice visual and you see all the proteins, but there are certainly other ways of detecting the protein, yeah. Oh, let's come back to that later, because I need to get you downstairs, but, yeah, it's another method that uses, an antibody, and then you just do a detection that's not running the cell, basically. Okay, so, let's go to, the protocols then. So, in experiment 2, we're running our mouse digest on a gel this morning. So remember, this was your mouse DNA that you cleaved with a variety of restriction enzymes the other day. And this is on page 98.